Hello, Darren here. Today we'll be continuing on from where we left off on the study design and talking about power functions. So, what is a power function? Now, a power function can be written as x to the power of something. We'll worry about transformations later on in other videos. Essentially, this power, as on the study design, is represented by q, which means all rational numbers. Now, that includes fractions, integers, negatives, all that jazz. To make things easier for you, we'll go through the main categories of power functions. So firstly, the power could be positive, it could also be negative, but we'll focus on the positive for now, and I'll talk about the negative towards the end of the video. So, with the power being positive, it could be a positive whole even number, or it could be a positive whole odd number. You see some examples on your screen right now. Now we could also have a positive fraction with an even denominator, or a positive fraction with an odd number denominator. Let's focus on a positive whole even number. So let's have a look at y equals x squared. The graph is that of a parabola, as you can see on your screen. Now the key points to note with basically all these graphs are when the x value is 1 and when the x value is negative 1. Have a think about the graph of y equals x to the power of 4. How would it compare to this graph? Using x equals 1 and negative 1 as your benchmarks, have a think about what might be different. So essentially, for x greater than 1 and for x less than negative 1, x to the power of 4 would be greater than x to the power of 2. That makes sense because you have a number like 3 or 4, and the more you multiply it by itself, the bigger it becomes. And the negatives just cancel out with x to the power of 4 or x to the power of 2, even if you start with a negative x value. However, between negative 1 and 1, x to the power of 2 is greater than x to the power of 4. The reason for this is that those numbers, those x values are all fractions or decimals, and the more you multiply a decimal by itself, the smaller the decimal becomes. If we fill in the parts where x is greater than 1 and x is less than negative 1, this is how x to the power of 4 compares to a parabola. And for x between negative 1 and 1, you see that x to the power of 4 is smaller than x to the power of 2. I'd like you to have a think about x to the power of 6 and x to the power of 8 and how they would look on this graph. In particular, what shape do you think x to the power of 100 would look like if it was drawn on these axes? And now we've covered that first class of power functions. Now let's consider power functions where the power is a positive whole odd number. We'll ignore y equals x to the power of 1 because that's just a straight line, and we'll start off with the next basic one, which is y equals x to the power of 3, which is a cubic. And a cubic looks something like this. Once again, we'll use the benchmarks x equals 1 and x equals negative 1 to help guide us to drawing the other power functions with odd powers as well. Let's consider the next one up, which is y equals x to the power of 5. For x greater than 1, x to the power of 5 would be greater than x to the power of 3, because the more you multiply numbers such as 4 or 5 by itself, the bigger it becomes. However, what changes compared to the previous scenario with an even power is the fact that for x less than negative 1, x to the power of 3 is actually greater than x to the power of 5. Now the way to think about this is that since x to the power of 5 is greater than x to the power of 3 for a positive number bigger than 1, since it's negative, everything is flipped. And the reason for that is 54 is bigger than 39, but negative 54 would be smaller than negative 39. And that's why starting off with a negative number less than negative 1 flips our scales. For x between 0 and 1, x to the power of 3 is greater than x to the power of 5. So whenever you have a positive fraction or decimal between 0 and 1, the more you multiply it, the smaller it becomes. And once again, for x between negative 1 and 0, the scenario is flipped because now we're starting off with negative numbers and we're ending up with negative results. And so x to the power of 5 is greater than x to the power of 3 in that interval. Now let's put the information we just discussed onto the graph. So for x greater than 1, x to the power of 5 is greater than x to the power of 3. And for x less than negative 1, x to the power of 5 is less than x to the power of negative 3. For x between 0 and 1, x to the power of 5 is less than x to the power of 3. And for x between negative 1 and 0, x to the power of 5 is greater than x to the power of 3. Okay, now let's consider the last two scenarios where the power is positive, and that is a positive fraction with an even denominator and a positive fraction with an odd denominator. We'll stick with the numerator being 1 for now. If it's 2 or 3, it's essentially still that fundamental graph. You still need to know what it looks like with the numerator being 1, and then consider what it looks like if it's been taken to the power of 2, or the graph has been taken to the power of 3. So how much bigger do the y values become? But anyway, we'll go through these a lot quicker because it's basically the same system, and I'd like you guys to give this a go yourself just to see whether you could do it. So try draw x to the power of a half and x to the power of a quarter on the same axes, and also try draw x to the power of a third and x to the power of a fifth on the same axes. Once again, the key point which will help you is when x equals 1 for the ones with an even denominator, and where x equals 1 and x equals -1 for the ones where there is an odd denominator. Okay, so your x to the power of a half should look something like this. It's a square root graph, so the x must be greater than or equal to 0. Now let's have a look at x to the power of a quarter. So for x greater than 1, x to the power of a quarter would be less than x to the power of a half. That makes sense because rather than square rooting a number, you're making it even smaller. Whereas between 0 and 1, x to the power of a half is less than x to the power of a quarter. Here's one way of thinking about why for between 0 and 1, x to the power of a quarter is greater than x to the power of a half. Let's take x equals 0.5. The y value we're looking for is a number which, for x to the power of a quarter, is multiplied by itself or taken to the power of 4 to give us 0.5. Whereas for y equals x to the half, if our x is 0.5, our y value is a number which, when multiplied by itself or squared, it gives us 0.5. So with fractions, the more you multiply a number by itself, the smaller it gets. So for x to the power of a quarter, we had to multiply the number by itself 3 times to give us 0.5, whereas for x to the power of a half, we only had to multiply the number by itself once to get 0.5, which means that that y value for x to the power of a quarter would be bigger because we had to multiply it more times to give us 0.5. An x to the power of a third looks something like this. And since this graph, you can have a negative x value, x to the -1 is quite important for us here as well. And your x to the fifth will look something like this. Same logic as we've been talking about the whole time. Keeping in mind that because of the odd denominator, it's flipped. So while x to the power of a fifth is less than x to the power of a third for x greater than 1, for x less than -1, it's the opposite, where x to the power of a fifth is greater than x to the power of a third. So going back to all these categories of power functions, we've looked at all of the positive ones, and now I'll just talk a little bit about the negative ones as promised. So keep in mind that a negative power can be rewritten as a fraction. So x to the power of -a is the same as 1 on x to the power of a. And you can see some examples here. With power functions with negative powers, there are two main ones that come up. The other ones are not that helpful. And they are x to the power of -1, which is 1 on x, or x to the power of -2, which is 1 on x squared. So let's have a look at y equals 1 on x. So with y equals 1 on x, we need to be wary of things called asymptotes. Now asymptotes tell us what things can't be. So looking at 1 on x, you should know that you can't ever divide by 0. So that means x can never be 0, and so we have an asymptote at x equals 0. Now another way of figuring out asymptotes is with limits. So let's consider what happens to 1 on x when x approaches infinity. So your denominator becomes really, really big, and your numerator stays as 1. And what happens when you have 1 divided by a really, really big number? It's really, really close to 0. And similarly, as x approaches negative infinity, you have a -1 on a really, really massive number, which is also really close to 0. So therefore, we have an asymptote at y equals 0. So let's draw those asymptotes in. And the graph of y on x looks something like this. When x is positive, 1 on x is positive. When x is negative, 1 on x is negative. So there are two things to note with this graph. Firstly is that as x approaches infinity and as x approaches negative infinity, y approaches 0, and you can see the graph approaching the asymptote y equals 0 on the right and on the left. But another thing that's really important is what happens to y when x becomes really small, both from the positive direction and also from the negative direction. And what happens is that when x becomes a really small positive number, 1 on x becomes really big. And when x becomes a really small negative number, 1 on x becomes a really big negative number. And that's why our graph looks like this. Now this graph is called a rectangular hyperbola. And the next graph is y equals x to the power of negative 2, or y equals 1 on x squared. And we'll go through a similar process of finding asymptotes. As you can see, the asymptote x equals 0 still applies because we still can't divide by 0. Once again, we consider limits. So what happens when x approaches infinity? It's 1 on a really big number squared, so really close to 0. And when x approaches negative infinity, it's still 1 on a really big number, which approaches 0. And the third thing we need to consider, like we did before, is that the smaller x is, the bigger 1 on x squared is. And so let's draw in the asymptotes, and then the graph. Keep in mind that regardless of whether x is positive or negative, 1 on x squared is always positive because you're squaring the x value. And this graph is called a truncus. A question to think about. Despite 1 on x squared being different to 1 on x, they both have a part of the graph in that first quadrant in the top right. I'd like you to think, how does the graph of y equals 1 on x squared compare to the graph of y equals 1 on x in that first quadrant? Good luck with your studies.